Nodal analysis. Nodal analysis is one of two generalized powerful circuit techniques to solve for currents and voltages. In this technique, we select a node as a reference node or ground, then we assign voltage names to the rest of those nodes, and these voltages are referenced to the reference node. We apply KCL to each one of these non-reference nodes, and we use Ohm's law to express the branch currents in terms of voltage. And after some simplification, we'll have some simultaneous equations that you can solve in general any way you would like. So let's take an example. And this example can be solved using our traditional methods of just summing R1 and R2 plus the parallel combination of R3 and R4, finding the total current, and then working our way backwards. And I suggest you do that as a check to the matrix method that we're going to do. Now, nodal analysis tends to do better with current sources, and so in this case I transform this voltage source to a current source. And you can see the current has been divided by this resistance, 0.2. I have R1 now in parallel with the current source, and the rest of the circuit is untouched. And if you want to see these circuits, you can cut and paste this link into the open file pop-up when you run LTSpice. So now we source transformed our circuit. We assign a node reference to all nodes not connected to ground. I will call that node 1. I will call that node 2. And this circuit too can be found just by pasting that link into your LTSpice open file browser. Now we're going to assign current names and directions. I1 is 0.2 amps coming into the node. I2 is coming across R1 this way. R3 is going through R2. R4 is going this way through R3, and I5 is going through R4. Now we're going to use KCL at each node. Since I1 is going into the node and I2 and I3 are coming out, I1 equals I2 plus I3. And now I3 is going into node 2, while I4 and I5 are coming out. Now we use Ohm's law for each branch current. And so I2 is simply V1 divided by R1. I3 is the voltage at node 1 minus the voltage at node 2 divided by R2. And I break it out here for something later. I4, it's V2 divided by R3, and I5 is V2 divided by R4. Now we substitute those relationships for current into the KCL equations. I have I1, I2, I3 KCL, I3, I4, and I5 KCL. And we plug it in, and we get here on the bottom I1 equals to 1 over R1 plus 1 over R2 times V1 minus 1 over R2 V2. And over here we have 1 over R2 times V1 minus 1 over R2 plus 1 over R3 plus 1 over R4 times V2 equals 0. And I'm putting it in this format for matrix manipulation on the next slide. And so if I look at this, I have I1 is a constant, which can vary in time, but it's something that's known. V1 and V2 are the variables, are the responses to I1. And this could be I2, but there is no I2 current source, so it's just 0. Now, there's an elimination method or the matrix method. And I investigated how important were matrix methods to the teaching of EE98, and what I found was most engineering faculty felt you needed to be able to do a 2 by 2 matrix on exams in follow-on courses, and you should be able to do a 3x3 for a homework. And as far as the E98 is concerned, I will show the matrix method, and there will be homework questions on this, but I tend to let you find your way to solve the problem. So let's convert it to matrix form and substitute the values. So these are the scaling factors of V1, and it goes in this position. Scaling factor of the first equation for V2, minus 1 over 2. In a similar fashion, 1 over R2 and minus 1 over R2 plus 1 over R3 plus 1 over R4. At this point, calculate the values into this matrix. Now, to really be able to follow this slide, you need to read pages 84 and 85 in the text, and maybe you should read the appendix as well. So first I calculate the determinant by cross multiplication. I get minus 0.302 milli, and then I have the determinant 1 of row 1, this determinant 1 and determinant 2, and then I can solve for V1 and V2 in this fashion. When I run this in Spice, I get the same values of V2 and V1. And this makes sense that V2 should have a higher potential, V1 should have a higher potential than 2. Now I have some thoughts on the matrix method. Is that you have to practice it a lot so that it doesn't take too long to calculate. And you have to really be able to do it in a quiet place where you can concentrate. Like I said before, 2x2 is expected on exams for most majors, 3x3 in homework for most majors. Anything larger than a 3x3, you should use MATLAB or IPython, which is a free software. Most of the syntax is MATLAB-like. And the matrix method is how LT-SPICE calculates these problems. In general, use the method you like best in 98. Of course, unless the assignment says use the matrix method. But I wouldn't want to pin you down on an exam. So I'd like to do another example of nodal analysis, but in this case we're not going to convert these